So first, thanks to the organizers for putting together this conference. It's very nice to be here in Marseille and not know 3/2 of the, of the room. It's very good to see new faces here. So I thought I could use the abbreviation random walk in dynamic random environment because you've all been very attentive to Daniel's course. And so that's another reason to thank the organizer, because they also offered me an introductory talk to my talk. So you're already kind of in the mindset that you know what kind of problem I'm going to speak about. So that's very good, always comfortable. So we are working with a random environment. So we have a eta t of x, and t is time, and x is in and x is in ZD. And for instance, maybe it takes values in 0, 1 to the ZD. You could imagine something more general, but already you have a lot of to deal with just in this setting. And you have on top of that, so this is an autonomous random environment defined by itself. And on top of that, you have your random walk. And the random walks makes plus or minus 1 jumps. And the way that it chooses whether to jump, sorry, nearest neighbors jump. We are in dimension 1, but not nearest neighbor jumps. And the way that you choose to which neighbor you are going to jump is going to depend on what you see under your feet, let's say, maybe around you, but for today, under your feet. So you have probability of x, so probability in environment eta of x n plus 1 going to x plus y, for a while a vector of norm 1, conditional on being at x at time n. That's going to be some function, some kernel, transition kernel, depending on y, so that's the probability to pick y, but the probability to pick y is going to depend on the environment under your feet, so it's going to depend on this environment process that Daniel introduced last time. That's, so the environment at time n at site x. And I'm sorry, I'm going to right away change my notation because otherwise it's going to be a mess later. I need eta for something else. This is omega. Omega is still indexed by n, that's okay. Okay, so far so good. And so Daniel told you already that a key player in this story is this process, this omega n of xn, which even if omega by itself is very simple, omega n xn, seen from this random walk that has collected a lot of information along the way, this is a complex object to understand. And it's complex because the position where you end up at time n depends potentially on the environment that you have around you at time n. That's exactly what Daniel was saying with the dimension 1 case. You remember that at time n, you were typically in a depth, in a well, in a trap of depth log n. Remember that? So knowing where you are tells you a lot about what the environment is around that. Okay. And so, okay, so that's a general feature of random walks in random environments. And why am I? So here we had the twist that the environment is dynamic. There are several reasons to do that. One first reason is that maybe it's just the model that interests you turns out to be dynamic, and then you have to deal with that. And that's actually my case. That's how I got into this business at the beginning. So why do we study dynamic random environments? So maybe it's your favorite model, which you're allowed to. There are more interesting reasons, at least theoretical reasons. One other reason is has to do with what Daniel explained about this picture of the potential that the random walk evolves in, which, okay, does not really, okay. And he said something like, okay, in static case, you have your potential and it's fixed, but if the environment starts to evolve, maybe the traps, those log n wells, they dissolve in the dynamics, and maybe all those features that we saw in the static case are going to go away. So that's turning the environment into dynamics is a way of exploring that, exploring how you can dissolve the traps in your environment. And okay. And another motivation that you might have is kind of okay, not the opposite reason, but is okay. A lot of known results about random walks in random environment are for the case where you have a lot of independence in omega. So the static case, we almost always take omega IID. And Daniel also hinted at the fact that even if no, never mind. So you always take omega IID. Even in that case, it's not so simple to study. But you might also want to deal with some correlated omega that also occurs naturally. And if you do that, you run very soon into a lot of trouble. Because if you, okay, you run very fast into a lot of trouble. And one way of simplifying things is to guarantee that even though your environment is correlated, you know that you're going to explore new regions. And one way of making that very, very strong is to say that you're always going down at least one step in a given direction, and we'll call this direction the time. So one other way of seeing this dynamic random environment is to say that we're actually not considering a random walk in dimension d, but in dimension d+1, which is very, very, very ballistic. And so that allows to explore other correlation structures in our environment, because we have gotten rid of the complicated problem of transients for the random walk itself. Okay, so I don't know how to write that. Explore correlated d+1 environments. With a very ballistic. Okay. Okay. So another standard thing that's already been discussed this week is that even though this process does not have, so Xn a priori does not have stationary IID increments, as we like to have in simple random walks. Nevertheless, there are situations, especially very ballistic situations, in which you can recover some hidden regeneration structure. So we saw this in a talk yesterday by Vittorio, I think, where if you are drifted to some direction, at some point you are going to reach a place which you've never visited before, and whatever you will visit after, you have never visited before. And if your environment is independent, then all the information of the future is independent from your past. So that gives you a regeneration time. And what we were trying to do in this project, so this is joint work with, so what I read just after, but what we're trying to do with this project is exactly to find this kind of regeneration structure, but with correlated environments. And I will not give I will not attempt to be, I want to focus on a specific example so it's clearer what we're trying to do. Correlated example in which everything is explicit. And yeah, and I'll tell you there. So this is joint work with Julien Allasia, who was our student with Augusto Teixeira, Random Baldasso, and Augusto Teixeira, who has been a long time complicit in this kind of questions. Yeah. Okay, so the example that I want to consider is Boolean percolation. So in dimension d plus 1. So I'm really in this kind of a framework in d plus 1. Z d plus 1 or d plus 1 doesn't really matter the exact definition. So what you want to have, okay, let's say RD. The random walk is going to walk on Z, just the environment you can imagine lives in R. So we want a Poisson point process phi of intensity. So the first coordinate is just you throw a bunch of points in the space. So that's RD plus 1. This is one dimension of time, and that is RD. So you have one intensity, which is Lebesgue in RD plus 1, sorry. And you also want another measure, nu, and nu is a measure, so that's on RD plus 1. And nu is a measure on radii. So the first part of my Poisson point process throws dots everywhere in RD plus 1, so if d equal 1 is the plane. And around each of those points, I'll draw a little ball of radius distributed according to nu, independent everywhere. So maybe I have some big balls or smaller balls, or bigger ball around this one, something like that. So I have a picture like that. And so far that's not an environment of this form. It's going to be, once I declare that omega t of x is just the indicator function. So now my points here have a coordinate in RD and a coordinate in time. So my environment says I am 1 if my point xt is inside a ball. One of those. So my environment is just 1 everywhere here. And 0 outside. And so I'm saying that this is a correlated environment. It's correlated because once you know that this is in the ball, well, this is also in the ball. Okay. If you have 2 points in the same ball, then the information this information is correlated. So the correlation in your environment is going to depend on the tail of nu. If nu has very light tails, then the different points are not going to see each other. But if you can have very large balls, then your environment becomes very correlated. So I don't want to make this statement precise, but just as an idea. So the correlations or the yeah. So the correlations depend on mostly on the tail of nu. And we're going to assume throughout that nu of rho infinity is something like rho to the minus beta for some beta. Okay. So we are looking for times at which we whatever we're going to explore after doesn't depend on what we've explored before. And what's really nice about this environment is that it's pretty clear what you have to do. What you have to do is, okay, so imagine you're at xt. What have you seen in the past? What you've seen in the past, so you remember time is still there. What you've seen in the past is whatever was living inside this cone. Okay? That's the cone of slope 1, starting at xt. So your past is certainly contained in there. So what you've seen in the past is whether or not the points in there were occupied, at most. So we're in a ball. What you see in the future is going to be whatever part of whatever is inside this cone. Okay. Good. So now, under what condition does the future not depend on the past? Well, it's just if those two things do not share a ball. So it's just, so if I have some ball like that, then it's, I cannot forget the information that I have seen here. On the other hand, if that does not happen, then I am in a good shape. So what I'm going to call eta now, that's why I had to keep the letter free. So now eta t of x is just going to be the indicator that no ball in my process touches both past and future. Okay, so that defines me a field over our zd plus 1, which is perfectly well defined. And it's not only well defined, it has very nice properties. So I claim that the field eta satisfied so the first thing that it satisfies is exactly what I built it for. It's that the future does not depend on the past. It does not depend on the past except for the fact that here we know that we have okay, it does not depend of the past if we are at a point where eta is 1. It depends only on the past through the fact that eta is 1. So the way that we formulated this is what gives the name to the title to the talk. The Random Markov Property says that for any xt, so you want to look at something that happens in the future. So something that, some event that is measurable with respect to omega in this cone. Omega in future of xt. You want to condition on everything that happened before. And by everything, I mean not only omega, which is here, but also the etas that I've observed there. And my claim is that this thing, if xt is such that eta t is 1, eta xt is 1, then that's equal to the same thing conditioned just on eta xt equal 1. So you can write it like this. Or yeah. Better like this. Sorry. Yeah. So that may not be the most natural formulation for this independence of past and future that you may think of, but it works well, and it works in other cases. So. And the second thing that and this is very easy to prove in that case. It's just the fact that Poisson point process charging disjoint sets are independent. Okay. Now, so I've assumed, okay. Yes, and now I need to say something about the triviality or non-triviality of my field eta. So one, okay, so the first reassuring property is that this field is non-trivial as soon as the beta is not too small. So if beta is larger than d plus 2, my field is, so it's stationary under translation, space-time translation, everything. So this is, this has positive probability. And moreover, so I had some correlation in my environment omega, which were depending on the tail of nu. Now what I claim is that they kind of transfer to a correlation in the decorrelation in the environment eta in terms of the tail of nu. And maybe the estimate is not optimal, but it's good enough for what we wanted to do. So what are we interested in? We want to, so we still have time there, always, still RD. And I have my field eta everywhere, and I want to say that if I look at boxes that are distant by some large number r, maybe, and maybe of size r, all. If I look at my configuration eta in here and in here, what I see is decorrelated in terms of this distance r. So I want to say that F1, so that's a box A, that's a box B. If I look at a measurable function of the eta restricted to a box A, and another measurable function applied to eta restricted to this other box B, then that's pretty close, and I actually need the pretty close in one direction. That's pretty close to the product. And there is an exponent which you can take to be 2d plus 1 minus beta. Okay. So all this is for beta reasonably large, but still polynomial correlations. Okay. Any questions so far? So that's no, something that I want to say before questions. So you notice that eta has an infinite range, right? So it's not completely obvious that you have this kind of decorrelation, because it's true that the eta here picks up information from there. Even if omega did not, it would still be okay. Let's not go there. But okay. But it's also true that the value of eta with high probability is going to be determined by only what it sees around it, around the point which you're interested in. Okay? If I want to avoid a ball meeting both this and that, and I check it in this horizon, then it's going to become very likely that it's also checked at further away from my point. So, okay, that's why you have to change the exponent, but why you also get the result anyway. Okay. Yes, what I wanted to say is that this is a decorrelation property in my eta. It's pretty weak compared to what you're used to in this business of random environment. It's only a decorrelation in covariance, right? not something uniform on the configuration or whatever, and it's only polynomial, even if it's with a reasonably high exponent. Okay, and so the result is that from there, what we can get so if you have those two things, and x is elliptic, I will discuss what I mean exactly by that. But if you have those two things and x is elliptic, then you can indeed build this sequence of regeneration times. So you have a sequence of random times, not Markovian, such that xti plus 1 minus xti, ti plus 1 minus ti. So that's IID. And the second thing, if beta is large enough, so large enough that this alpha is useful, you have a tail on this increments. Tail estimate that says, sorry, it's not IID per se, it's IID under, yeah. It's IID under the modified measure that you condition to have eta equal 1 at the origin. So under the probability conditioned on eta 0, 0 equal 1. So you're just conditioning on an event of positive probability, but you have to do that in order to have something stationary. And so the last thing is that for beta larger than 2d plus 1, the expectation of set t1 minus t0 to the gamma, conditional on that, yeah, that's finite. For any gamma smaller than whatever this is. Okay. Okay, and once you have this, then you're happy, because then essentially, if you can take gamma large enough, you have. If you can take gamma equal to 1, you have a law of large numbers, and if you can take gamma equal to 2, you essentially have a CLT, and so on and so on. This is pretty standard. Okay. So I'm not going to discuss. I'm not going to discuss all the proofs. So normally, what you do in a research talk is you explain how what you've done is so very different from what you've done before. And today I kind of want to do the opposite. So what I would normally do is comment more on the random Markov property, why we formulate it like that, why it implies this IID decomposition, which is not completely straightforward, even though it's kind of intuitive. So the first part of the proof that we will all agree with is that you want to define at least the first time is 0, and you want that T1, so under this condition measure, which should have given a name to. So this is P hat. Okay. So under this measure, I want T0 to be 0, and T1 would be the first time that you hit a point where eta is 1. So it's the first time where you forget your past. It's why I built eta that way. Okay, so that first part is fine. The other part is a bit more tricky, but we'll not discuss it today. What I want to do is show you the kind of boring part, the part where we show the tail estimate. It's not so boring, but it's actually very similar to what we've done in many other papers. So with Augusto, and also Julien in his PhD did a lot of this technique. And it's kind of always the same, but I think it's useful in a research school to show you something that works in different contexts. So let's do that.
So in general, you just say, I have some eta that satisfies these properties. And then
Yes, so the theorem is if my eta satisfies this, then I get the result. And then in this example, I built eta so that it satisfies this property.
And is it easy to verify this decorrelation property for that example? Or?
For that example, yes. No, that's what I said. That so you have to restrict to a large box, show that the version where you only want no ball intersecting the truncated cones exists, and then you show that with high probability this version and the real eta coincide. Okay, it's straightforward. No, but it's the only thing that you can imagine, no? You have something infinite range, you truncate it, you show the decorrelation for the truncated version, and then you show that it carries through the non-truncated version. No, so that's okay.
And you don't need any small disorder thing like in static environment, for statics when you want to have integrability of the random times, so you need some conditions, you know, if it's it's because you decorrelate.
Yes, it's because I've chosen my drift to be 1.
Okay.
Yeah. Okay. So what I claim is that if you look through our papers with Augusto and Julien's paper in the past, there is always at some point this argument that if you have a field of interesting points, and the interesting points here are those where eta is 1, so you have a field of points that are nice, that help you. If this field has a positive density and is decorrelated in the sense that I stated there, then, and your walk is elliptic, then any then your random walk is going to meet a lot of those points. So that if you have a nice field of helpful points, so that would be the set where eta tx is 1, with positive density, decorrelated in the sense above, an elliptic random walk meets one of them quickly. It's actually going to meet a lot of them. Okay, so I want to explain this. And it's interesting because if you have this in mind, then in some sense you just have to think of what it means to be a helpful point. So depending on the question that you ask, the result that you want to prove, you just have to find a good enough definition of your eta that helps you prove what you want. Okay? And then, okay, the rest is going to depend on the specifics, but this mindset already kind of takes care of disentangling this omega n xn. Okay, you reduce the problem to finding good spots in omega, and then the random walk is going to take care of itself. Okay. So the first step in this proof So the first step is that, so where does the ellipticity help you? It helps you to increase the density. So what do I mean by that? So here, eta, a priori, could be very, very sparse. I've only said that it has positive probability of being 1. Does not need to percolate, it does not need to do anything like that, right? You can perfectly build a trajectory that completely avoids your set eta. But there is a way of making your set eta, your set crosses, look bigger from the point of view of the random walk. And one way to make it look bigger is to say, every time I have a point where eta is 1, so my claim is that if I look at a cone of a height h, and somehow my random walk lands somewhere here, then it's going to, with positive probability, it's going to be able to travel to that point. With positive probability, that does not depend on what the environment here is. So let me explain that. If you've never seen that, so ellipticity here, it can mean a lot of things in this in the random walk in random environment business, but here it means that no matter what omega is, no matter what y of a nearest neighbor of the origin, the probability p that I had at the very beginning, the probability seeing the environment omega to jump to y, that's strictly between 0 and 1. And what that tells you, okay, so
Well, in this case,
yeah.
wouldn't it, I mean, I would call this uniform ellipticity just because we have finitely many.
If you like, yes.
Okay.
Yeah. So now you wait. Yeah, it's uniform. So it means that in particular, this is in fact between some kappa, 1 minus kappa, if you like. So what I want to say is that there is a way to build this random walk in random environment by looking at the environment, sampling a uniform random variable independent from all the rest. And depending on where this uniform lands in the interval 0, 1, you are going to apply some instruction. And the decomposition of 0, 1, so say we're in dimension 1, you have the probability to jump right. You remember that this would be P1, 1 in dimension 1. So the probability to jump to the right, that's what Daniel denoted by P full before. And you have another probability, maybe here, P, a probability to jump to the right when you are on top of an empty site. And the kappa is maybe here. Okay. And this is 1 minus kappa. And if your uniform lands here, then you know what you have to do. You know here that you have to make a +1, and here you have to make a -1 jump. Okay? And you don't need to look at the environment to do that. That's the important part of the thing. So, okay, so with this in mind, if you know that some trajectory that your random walk might follow meets a lot of these of points that are at the basis of a cone issued from a cross, then this uniform ellipticity tells you that at some point you're going to succeed in exactly following this path, and that's not going to give you any information on the environment. Okay, so it is enough to show that any path meets actually a lot of cone bases. For H large. That's fixed. So that's my goal now, that's a new goal. I want to increase my H and stop when it becomes very likely that any path, really no matter what I do, any allowed path that respects the nearest neighbor jumps, meets a lot of the points that are on a place like this. So let's see how we can do that. So the step 2 is to show that this does occur. And that's a multi-scale argument. Okay, so what we're going to do is first to say, I want to do something simpler. So I want to do something simpler. I want to take a big vertical segment of size L, and I want to say that with high probability, somewhere here there is a cross. Okay. So let me fix. It's a simple multi-scale argument, so which is why I'm giving you it, because it can get ugly very fast in this business, but not here. So you fix L to be 4 to the k, which is a simple enough progression, very increasing very rapidly. And I say that okay, my notes is very, very poor, but it's okay. The probability that eta, let's say at 0, at time 0, at time 1 equal eta at time L k 0 equals 0. So I have no cross on my stick of length Lk. Okay, so that's this probability. And I want to argue that this is very small. And the way that I want to argue this is to say, okay, if this is true at scale k plus 1, then it has to be true. I don't know why we put 4 here, actually. So if I have no cross there, I need to have no cross there, and no cross there, and no cross there, and no cross there. And okay, that's something. But I'm only going to use that it means that we have no cross here, and no cross here. And now those two things, they only look at eta in separate boxes, and the boxes are separated by 2lk. So I can use my decorrelation hypothesis to say that this is smaller than actually pk squared plus something that depends on lk, that decays with lk. Okay? And you've all met in your studies this recursive equation, inequality. And you all know that if you start from a pk naught, small enough. So you have this. Okay, this would be y equal x squared, and this is y equal x. If you start from a pk naught that is below this threshold, then what am I doing? Yes. Then your pk goes to 0 very, very fast. It's also kind of true with this error term, but you have to work a bit more to make it work. Okay. And what I claim is that, indeed, if you work a little bit, you can get to the fact that this pk is going to decay essentially like, I should have written that. I think it's going to decay essentially like this. So it doesn't work right away. You have to do it in 2 steps, but it's a bit okay. So again, my goal is to convince you that we know that there exists a strategy to help us prove this, and then you have to work out the details in the given situation where you are, but you know that it's going to work. And then you have to finish the argument, and I'll stop there. But the next, so that's actually two multiscales in one, if I'm more honest with you. The step 3 is essentially the same, but it's going to say now that I have a good probability of finding a cross somewhere on my stick, I want to show that I hit the basis of a cone with good probability. And the way that I'm going to do that is to draw a cone and to look, I'm drawing. Draw a cone and look for a cross somewhere on this stick. If I have a cross somewhere on this stick, then starting from any point here, I can reach it. Okay? And I want to argue that if I draw my picture like this and I color this basis green, then any path is going to meet grid points, a lot of grid points. And then that's where you have to be to do a multiscale that is not so simple, but you want to look at the event AKH. So that's for H large enough. And your bad event here is that there exists a path that avoids, that meets less than, so we took k square, never mind, green points. And if this occurs at scale n plus 1, so you find your path, and it doesn't meet a lot of green points, then that means that also you can find 2 smaller boxes in which this thing happens. That's the cascading property. And then what you end up with is the same kind of recursive equation. So the pKh is going to be smaller than, so you have this time a C that is counting the ways that you can choose your sub-boxes. pKh squared plus Lk minus alpha. And then that's it. Essentially, you get to your end result by using H to push a pk0 to something small enough, and then everything takes care of itself. I think it's time I stop.